In section 7, we're going to talk about the following idea. When we have a big Markov chain, it can be convenient to study it by splitting it up into smaller pieces and studying those smaller pieces separately. Those smaller pieces we call classes or communicating classes. The idea here is if you've got two states, I and j, if it's possible to get from I to j, maybe not in one step, maybe in a bunch of steps put together. And then if you can also get from j back to I again maybe in a number of steps. If that's true, that we can get there and back, I and j ought to be in the same piece of the Markov chain, in the same communicating class. On the other hand, if you can't do this, get from I to j and back again, then we can probably allow those to be in different pieces, in different communicating classes. So let's look at a formal definition here of what we're talking about. Okay, so here's our definition. Definition 7.1 here says we say that a state j is accessible from a state I, and we write this I arrows j here for that, if for some n, pijn is strictly greater than 0. So that means we can get from I to j. In particular, there's some n where we can get from I to j in n steps. So it doesn't have to be directly from I to j. It can be I to somewhere else, to somewhere else, to somewhere else, to j. If we've got that path from I to j, then we say j is accessible from I. And then the second point here, if I arrows j and j arrows I, so we can get from I to j and we can get from j to I, we say they communicate with each other. We write that with the double-headed arrow to say that I arrows j and j arrows I there. So that's the idea. If there's some n such that pij is strictly greater than 0, we can get from I to j. If there's some other n such that pji n is strictly greater than 0, then we can get from j to I. And that means they ought to be in the same piece of our Markov chain. Okay, so we've defined this communicates with relationship, this double arrow. Because we're mathematicians here, we ought to be thinking, what can we prove about it? And here's something we can prove about it. We can prove that it's an equivalence relation. So hopefully you remember from a previous course last year what an equivalence relation is. But in case you've forgotten, there they are. They're the three properties you have to be an equivalence relation. You have to be reflexive, symmetric, and transitive. Reflexive, meaning that I double arrows itself. Symmetric, meaning if I double arrows j, then j double arrows I. And transitive is the kind of step-through property. If I double arrows j and j double arrows k, then you can shortcut out the j and say that I double arrows k. Okay, so let's have a go at proving this then. So let's do reflexive first. So, does I communicate with I? Can we get from I to I in some number of steps? Well, yes, we're already there. So we can get there in 0 steps, can't we? So P, I, 0. Probability we go from I to I in 0 steps. Well, that's 1. And 1, last time I checked, was greater than 0. So that 1 is done. That was easy. That's enough to show that I communicates with I. Symmetric. Symmetric is easy as well, right? Because if we look at this definition, we say that I double arrows j if I arrows j and j arrows I. But that's obviously equivalent in swapping j for I. That just means we've written them in a different order, but it's obviously the same definition. So symmetric is so obvious I don't think we need to write anything down. So transitive is the only one where we've actually got something to prove. So let's do it in one direction first. Suppose I goes to j and j goes to k. We need to show that we can get from I to k. Can we do that? Well, yes, we could take the route that goes via j to get from I to k, right? If we wanted to get from I to k, we could get there by going via j. So we just need to be a little bit clever to write that down in mathematics. So if I arrows j, what that tells us in mathematics is that there's some n such that pijn is greater than 0. And if j goes to k, that tells us there's some, well, we better give it a different letter this time, and let's call it M. So PJKM is greater than 0. That's what it tells us by definition. So if we can get from I to j in n steps, we can get from j to k in m steps, then if we go from I to k via j, we'll do it in n plus m steps, right? The first n steps will take us to j, the final m steps will take us to k. So this is what we want to look at. We want to look at the probability we get from I to k in n plus m steps. And if we can show that's strictly positive, we're done. Well, if you think back to 2 sections of notes, back to section 5, we saw a result about things that look like pik of n plus m, didn't we? The result we saw was what we called the Chapman-Kolmogorov equations. Perhaps you need to pause the video and just go back and check what the Chapman-Kolmogorov equations were. But they said that a route from I to k of length n plus m is a route from I to somewhere. We're already using the letter j, so let's say L. I to L in n steps plus L to k in m steps, and that is summed over all L. That was the Chapman-Kolmogorov equations, which I'm abbreviating to CK there, the Chapman-Kolmogorov equations from section 5. Okay, so we've got this sum over all L, PIL, PLK, but all those terms are non-negative, so we can just pick out one of the terms from the sum to get a bound, can't we? We can say that this is greater than or equal to picking out a particular element of the sum, and quite predictably we're going to pick out the L equals J term, where J is this J here from above. So just from picking out a single term from the sum, the L equals J term, we get that this is bigger than Pijn Pjkm. But we've just proven up here that those terms are both strictly positive, so when you multiply together 2 strictly positive things, you get a strictly positive thing. And so Pik n plus m equals 0, so there exists some time, and that time is n plus m, so we get from I to k. So therefore, I arrows k. And same argument in reverse gives us k arrows I. Right. How do we get from k to I? We go via j. We can get from k to j by hypothesis. We can get from j to I by hypothesis. We can use the Chapman-Kolmogorov equations in the same way. And if I arrows k and k arrows I, then they communicate with each other. And that proves transitivity. So that one required a little bit of work, but it was putting together the common sense idea that if you can get from I to j and j to k, then you can get from I to k, and you take the route that takes you via j. And that's what we just proved there. Okay, so we've proved that this thing is an equivalence relation. And if you remembered about equivalence relations, you perhaps also remembered another fact about them, which is an equivalence relation splits your space into equivalence classes. An equivalence relation, I'm going to use the word partition space into equivalence classes. So here our equivalence relation is the double arrow. Our space is the state space, which we've normally been calling curly S. And equivalence classes here we call communicating classes, because they're the ones that satisfy the communicates with relationship. So what that means is that if we put together like a bunch of states that all communicate with each other, we get a communicating class. And every state is in exactly one communicating class. It's not in 0, not in 2, not in 3, it's in exactly 1. And those communicating classes are what we get when we bunch together all the classes, all the states that communicate with each other. So to write that out, the communicating class for the state I is all the states j such that I communicates with J. I say, so once you pick I, you pick all the things that communicate with it, and they all communicate with each other by transitivity, and you've got this kind of blob in your graph, which is a communicating class. Now that's quite a technical and like mathy definition. I think everything will be clearer if we start looking at some examples. So once we've got some examples, I think it will become clear what this means. So I'm going to start with my favourite example of a Markov chain. So I think you know what that's going to be. It's going to be the simple random walk, my favourite Markov chain. And I'll assume that P isn't 0 or 1, because it's silly when P is 0 or 1. So here, well, every state communicates with every other, right? Because if we want to get from 2 to 7, you have to go up 5 steps, which might happen. It happened with probability P to the 5. If you want to get from state 11 to state 4, you have to go down 7 steps. That happens with probability Q to the 7, so that's positive. So basically, from any state, we can get to any other state just by going straight there with some positive probability. It might be a very small probability, but it's certainly positive. So every state is accessible from every other state. Which means that every state communicates with every other state. Because you communicate with if you just are accessible in both directions. So that means the whole state space is a single communicating class. Whole state space, which here is the integers for the simple random walk, is one communicating class. So actually we can't split up the random walk into smaller bits really. Everything's in the same bit in the simple random walk, because you can get from any state to any other state. Okay, what about a slightly more complicated example? Well, my second favourite discrete time Markov chain is the gambler's ruin. Again, with P not equal to 0 or 1, because that's silly. So remember that the state space for this is 0, 1, 2 to m minus 1 up to m. Because when Alice has 0 money, she's ruined, and when she has m money, she's won all Bob's money, and Bob is ruined. So the first thing to see is that 0 and m are kind of special cases here, right? Because when Alice has 0 money, she's ruined, and she stays at 0 forever, right? So once you hit 0, you can't get anywhere else. So no other states are accessible from 0, because once you're at 0, you stay at 0. So 0 doesn't communicate with any state. So 0 is a class by itself. So 0 is a class by itself because the chain stays there. But then, of course, the same is true of the state m, right? Once Alice has m pounds, she's got all the money and the game stops. So the Markov chain stays at m forever. So no other states are accessible from m. So no other states communicate with m. So that is also a class by itself. On the other hand, what happens in between there? Well, until we hit one of the edges, we're just doing a simple random walk, right? We're going up and down, simple random walk. And so in there, we're in the same state as before, that everything is accessible from everything else, so everything communicates with everything else. So that is also a class. So in the gambler's ruin, we have 3 classes. We have the class 0, we have the class m, and we have the class of everything else, because everything else communicates with each other, but 0 and m, once we get there, we stick there. Okay, let's not stop yet. Let's look at another example. Here's one I prepared earlier. I made this simple model of an illness where you have 3 states. You can be healthy, you can be sick, or you can be dead. And so in this Markov chain, which you can see here, if you're healthy, you might stay healthy, or you might become sick. If you're sick, you might recover and become healthy. You might remain sick, or you might die. But if you die, you stay dead, and you stay in the death state here. Okay, so I think the first thing we notice here is that the dead state is once you're there, you stay there, right? So no other states are accessible from being dead, so no other states communicate with being dead. So that is a communicating class by itself. But healthy and sick, you can get from healthy to sick in one step, and you can get from sick to healthy back in one step as well. So that is that's a communicating class with two states in it. So in this healthy, sick, dead chain, we have two classes. We have the dead class and we could call it the alive class of being either healthy or sick. Okay, so hopefully those examples have made it a bit clearer what these communicating classes are. They're the bunches of states that all communicate with each other. So it will be useful before we finish on this to have a few more definitions. So the first one here, if an entire state is one communicating class, we say it's irreducible. So irreducible kind of means we can't break it down into smaller bits because the whole state space is one communicating class. So we can't break it down into smaller bits and it's irreducible. Second one here, a communicating class is closed if no state outside the class is accessible from any state within the class. So in other words, that means that once you get into the state, you stay there. So closed is once you get into the class, rather, you stay there. And if it isn't closed, we call it open, which seems like a totally reasonable word for something that isn't closed. And then finally, this last definition, if you've got a communicating class with just one state in it, and that class is closed, then we say the state is absorbing. So absorbing is the special case of closed, where the class only has one state. And that means once you get into the state, you stay there. Okay, let's go back to the examples we were just looking at and see if we can spot any irreducible, closed, open classes or absorbing states. So where were we? Started with the simple random walk over here, didn't we? And we said that the whole state space is one communicating class. So that's irreducible, right? Irreducible if the whole state space is one communicating class. And obviously if there's only one communicating class, once we get into the class we don't leave it. So that communicating class is also closed, irreducible, and by necessity closed. Okay, what about the gambler's ruin? Well, we said that for 0 and m, once we get to those states, we stay there. So those classes are closed and those states are absorbing. Again, with m, once we get there, we stay there, so that class is closed and that state is absorbing. Whereas this class from 1 up to m-1, we can leave that class, right? Because if we go from 1 down to 0, we leave the class, or if we go from m-1 up to m, we leave the class. So that class is open, and because we had more than one class, this was not irreducible, because we could break it down into 3 smaller pieces. Okay, what about a healthy, sick, dead chain? Well, the death class over here, that's closed, because once you're dead, you stay there. And because it's a class with only one member that's closed, that means it's absorbing as well. So the death class is closed, and the death state is absorbing. Whereas this healthy, sick class over here, we can leave it, right? We can leave it by taking this edge and dying, so that this is an open class. Again, because we have more than one class here, this is not irreducible. So just to say that these definitions of irreducibility and being closed or not will come up again quite a lot in the course, so you need to learn them. But next we'll do another property of Markov chains that will come back to classes.